Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. The domain name system is a distributed and hierarchical system responsible for resolving host names into numerical IP addresses. This system makes it possible for users to access websites and services using readable names rather than difficult-to-remember numbers. DNS operates primarily over UDP port 53, offering a lightweight and efficient method of communication. At its core, it provides a user-friendly interface for accessing both public websites and private network resources, forming a foundational element in every networking environment. There are two primary types of lookups used in DNS: forward and reverse. A forward lookup is the most common, translating a domain name like example.com into its corresponding IP address. In contrast, a reverse lookup starts with an IP address and returns the associated domain name. This reverse process relies on pointer or PTR records. Both types of lookups are essential in different scenarios, and understanding the distinction between them is necessary when evaluating network behavior or conducting forensic analysis. The DNS query process involves several layers of interaction. When a client initiates a query, it sends the request to a resolver, often maintained by the Internet Service Provider or internal network. The resolver, in turn, contacts root servers, top-level domain servers, and finally, the authoritative server responsible for the requested domain. Once the correct IP address is found, the resolver returns it to the client. This layered approach helps distribute the load and improves efficiency and redundancy across the global DNS system. Each part of the DNS resolution path serves a specific role, and exam questions may ask which type of server holds which responsibility. The resolver performs recursive queries on behalf of the client, the root server handles top-level domain redirection, the TLD server narrows the search to the correct authoritative server, and finally, the authoritative server delivers the IP address mapped to the requested domain name. Being able to follow this flow step by step is key to understanding the full resolution process and answering layered exam questions. Various DNS record types serve different functions during the resolution. The A record maps a host had to an IP version 4 address, while the AAAA record does the same for IP version 6. CNAME records provide canonical name aliases which are useful for redirecting domains. MX records designate mail exchange servers used in email delivery. Understanding the purpose of each record type is essential for interpreting zone files and troubleshooting resolution issues, especially when services are misrouted or unreachable. Other records, like SRV, TXT, and NAPTR, also appear in specialized configurations. The SRV record helps in identifying services running on specific ports, such as for VoIP or messaging applications. TXT records are used to store arbitrary text, often related to email authentication. The NAPTR record is used in voice and messaging protocols to map phone numbers to domains. While these may not be as common, their purpose and structure can still appear on the certification, especially in questions about advanced service records. Two additional record types that serve administrative roles are the NS and SOA records. The NS, or name server, record specifies which servers are authoritative for a particular domain. The SOA, or start of authority, record provides metadata about the domain, such as the primary name server, the email address of the administrator, and serial number information. These records are used during zone delegation and at server startup to ensure accurate synchronization and responsibility across the DNS hierarchy. Understanding how the SOA record's serial number works is important for managing zone transfers. When a change is made to a zone file, the serial number is incremented, signaling to secondary servers that a new version is available. If the serial number remains unchanged, the secondary server assumes that no updates are necessary. This mechanism plays a central role in maintaining consistency and avoiding outdated or conflicting DNS data between multiple servers, which is a point of emphasis on the exam. Time to live, or TTL, is a value associated with every DNS record that tells resolvers how long they are allowed to cache the data. This setting helps reduce repeated queries by storing previously resolved addresses locally. A shorter TTL means records will expire quickly and update more frequently, which is useful when changes are expected. A longer TTL reduces query traffic but may result in outdated information lingering after updates. Understanding how TTL impacts caching is vital for troubleshooting slow propagation or outdated responses. You may encounter questions on the certification that involve propagation time after a record update. If a domain's record changes but clients continue to reach the old IP address, a long TTL is likely the reason. In these cases, understanding how to lower the TTL temporarily before a planned change can help avoid delays. This concept of propagation delay and cache expiration is central to many real-world resolution issues, and it can be tested through troubleshooting-based scenarios on the exam. Queries can be recursive or iterative, and both styles have distinct behaviors. In a recursive query, the resolver takes full responsibility for tracking down the final answer and returning it to the client. This method is commonly used by end-user devices, offering convenience and speed. In an iterative query, the resolver responds with a referral to another name server, and the client is expected to follow up. While more efficient for system-level communication, iterative queries place more load on the client. Recognizing the differences helps in understanding resolver behavior under different configurations. Most public resolvers use recursion by default to provide complete answers to users quickly. However, understanding how iterative resolution works can help explain why some internal tools or systems respond with referrals rather than final answers. This distinction between recursive and iterative modes can be important in diagnosing misconfigurations or resolving failures that involve third-party DNS providers, particularly when firewalls or filtering mechanisms are in place. The DNS resolution path includes multiple layers of name servers. The root servers are the starting point directing queries to top-level domain or TLD servers such as .com or .net. These TLD servers then direct queries to the authoritative name servers responsible for the domain in question. Only the authoritative server can provide the final IP address. This hierarchical approach ensures fault tolerance, distributed load, and a clear chain of responsibility. On the exam, you may be asked to identify which server provides which part of the answer. There are 13 sets of root name servers distributed globally, each identified by a letter from A to M. These root servers do not hold information about individual domain names, but they know how to direct queries to the correct top-level domain servers. This tiered structure allows for massive scalability while maintaining consistency. Knowing how each level of the DNS system works together supports both conceptual understanding and accurate troubleshooting in layered network scenarios. Zone files are the configuration files used by DNS servers to store record data. These files include all the necessary entries for a domain, such as A records, MX records, and NS records. When multiple servers are used for redundancy, zone transfers copy the content from a primary server to a secondary one. This process is typically done using the AXFR protocol and can be restricted by IP address or secured using TSIG keys. Understanding how zone transfers work is critical for maintaining consistency and security in enterprise environments. Improperly secured zone transfers can lead to data leaks or unauthorized access to internal domain structures. This is why many administrators restrict transfers to specific IP addresses and apply authentication mechanisms. The certification may include questions that reference open zone transfers as a vulnerability or that require identifying the appropriate protocol for transferring records securely. Being familiar with these techniques will improve your ability to answer questions related to both service availability and DNS integrity. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. Internal domain name system servers play a crucial role in resolving names for devices and services that exist within a private network. Instead of sending every name query to the public internet, internal DNS servers handle requests for internal host names, such as local file servers, printers, or intranet sites. These servers are usually part of an organization's Active Directory or enterprise infrastructure. They often forward unresolved queries to external servers, allowing a seamless combination of internal and external name resolution, while maintaining control over local records and access policies. Public domain name system services are widely available and provide fast, reliable resolution for internet-bound queries. Popular public resolvers include those operated by Google, Cloudflare, and major internet service providers. These resolvers typically support recursive queries and are optimized for speed and global reach. Some organizations configure their systems to fall back on public DNS if internal servers fail or to override local policy. While public services are convenient, using them exclusively may expose queries to external monitoring or create mismatches with internal resolution requirements. Split horizon DNS is a configuration technique where different answers are returned to clients depending on their location or network interface. This method allows the same domain name to resolve to an internal address for employees connected to a private network and to a public address for users on the internet. Split horizon is essential in environments that use VPNs or network address translation, ensuring that clients always reach the correct internal or external version of a resource. It is implemented by creating separate views or zones on the DNS server. This setup prevents issues like hairpin routing, where internal clients are mistakenly directed out to the internet and back in again to reach local services. On the exam, scenarios may ask you to identify when split horizon is appropriate or to troubleshoot resolution failures caused by missing internal records. Knowing that separate views must be configured to support split responses is important when diagnosing why internal clients cannot access resources by name. Dynamic DNS is a feature that allows hosts to update their own DNS records automatically, typically as part of DHCP integration. When a device joins the network and receives an IP address from the DHCP server, it can register its hostname and address with the DNS server without administrator intervention. This keeps the DNS database up to date in dynamic environments where devices frequently connect, disconnect, or change addresses. Authentication is often required to prevent unauthorized updates. This mechanism is especially useful in large enterprise environments and supports centralized name resolution for mobile users, remote workers, or IoT devices. The exam may include questions about dynamic updates in scenarios where DHCP and DNS integration is required. You may also be asked about the need for secure updates, which protect against spoofing or hijacking of names by unauthorized devices. DNS security extensions, known as DNS-SEC, add a layer of trust to the DNS process by digitally signing records. This prevents attackers from poisoning the cache of a resolver with false information or spoofing domain responses. When DNS-SEC is enabled, each record includes a signature that is validated against a public key. If the validation fails, the resolver rejects the response, ensuring the authenticity and integrity of the returned data. While DNS-SEC does not encrypt queries, it ensures they have not been tampered with. Implementation of DNS-SEC can be complex and requires both the domain owner and the parent zone to support the feature. Despite its challenges, DNS-SEC is an important tool for preventing man-in-the-middle attacks and protecting users from malicious redirection. On the certification exam, you may be asked to identify the purpose of DNS-SEC or to recognize when its absence could result in a vulnerability. Common DNS issues can manifest in various ways. If a name does not resolve at all, it may be due to a missing record, incorrect zone configuration, or a failure in the resolver chain. If the wrong or outdated IP address is returned, caching or propagation delays could be to blame. An unreachable DNS server may result in timeouts or fall back to secondary services. Misconfigurations in TTL values, incorrect forwarding, or split horizon errors can all contribute to unpredictable name resolution behavior. The exam may include troubleshooting scenarios that involve reviewing logs, interpreting command output, or recognizing symptoms of typical DNS problems. Being able to associate symptoms with their underlying causes is key to choosing the right steps for resolution. For example, if clients intermittently receive the wrong IP address, a long TTL or stale zone file may be responsible. If no clients can resolve a domain, the authoritative server may be down or misconfigured. Several tools exist to help diagnose DNS behavior. nslookup and dig are command line utilities that allow manual queries of DNS records. They can be used to test individual record types, check resolver paths, or confirm authoritative answers. Ping is often used to verify whether a resolved IP address is reachable, although it does not confirm DNS functionality by itself. Traceroute helps determine the path traffic takes to reach a destination, identifying potential bottlenecks or routing issues. Each of these tools plays a role in pinpointing the source of DNS failures. On the exam, you may be asked to interpret sample output from nlookup, or to choose the best tool for a particular situation. For example, if a record exists but the address is not reachable, ping or traceroute would be more useful than dig. If a client resolves a name to the wrong address, using dig to query multiple name servers may reveal inconsistent records or missing updates. Topics on the exam related to DNS cover both conceptual understanding and practical skills. You will be expected to match record types with their correct usage, such as knowing that MX records handle email routing and that AAAA records map to IP version 6 addresses. You will also need to understand the flow of a DNS query from client to resolver to authoritative server. In troubleshooting scenarios, you may be required to identify misconfigurations, caching issues, or server failures that prevent name resolution. Questions may also test your understanding of recursive versus iterative queries, the purpose of zone transfers, or the implications of using public versus internal DNS servers. Being able to apply this knowledge in context will be critical for success on the test. Familiarity with tools, protocols, record types, and configuration concepts will help you navigate a broad range of question types and formats. The domain name system is an essential service that supports virtually every aspect of modern networking. By translating domain names into IP addresses, DNS enables seamless communication between users and services. Its distributed structure, reliance on multiple record types, and support for both public and private networks make it a critical area of study for the certification. Future episodes will continue to build on this foundation as we explore deeper network services and their supporting protocols. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.